Welcome back. Today we're going to be starting section 3.2, talking about domain and range. This is going to be a continuation of our chapter on functions. A quick reminder, hopefully you are reading through your textbook, trying the try-its in the blank notes, reading through the completed notes to see where you can get help, watching these videos to learn about the material, and then practicing your homework questions so that you're prepared for the test that comes up at the end of chapter 3. A reminder, if you have any questions or need any help or need help understanding something, you can always reach out to your instructor who's happy to help you. All right, let's get started. So today, talking about domain and range, I thought it was fitting. Our Bible verse for the day, Psalm 16:6 says, "Your boundary lines have fallen for me in pleasant places." Some other verses say, your boundaries of inheritance have fallen to me in pleasant places, and I will delight in the inheritance of the Lord, or I will delight in the Lord. And this is just an idea, I think, as we talk about boundaries and we talk about domain restrictions and places where lines are drawn, and we say this is the restriction around this thing, that our restrictions are around the numbers and the numbers that we're working with in these functions. But in life, this principle of restrictions is all over the world. And the Lord has restrictions, and the Lord has boundary lines for us, and they are good, and they are true, and they help us. So just like the Lord's boundaries help us today, domain restrictions help us on a much, much smaller scale. So we're going to talk about domain and range. You'll see at the beginning of this chapter in your textbook and in the notes, you have a chart. We went over this chart together, I think in the last session in 3.1 functions. But this is a chart that just teaches you a little about how to write inequality notation, interval notation, a description in words, and to put it on a number line. So just all the resources to get these intervals down. All right, so let's get started with domain. So try-it 1 says, find the domain of the function. And here we're going to define domain and use this definition for the entire day. So domain simply means X values or input values. Either one of those is a good way to think about it. I like to ask myself the question, what can X be? Is there anything that X cannot be? Like in chapter 2, we saw there were a lot of times when X could not be 0 if it was on the bottom. Or if you have a square root, you can't have a negative number on the inside. And so we have restrictions in math that we place on things. And that's kind of this idea of domain. We're asking, what are the X values? What are the input values? And so here we have a few X values in a list. And to write a domain, we're just going to list those in a set. -5, 0, 5, 10, 15. And close the set. And that's it. That is the domain of that set of points. So not too crazy, hopefully. Hopefully it looks pretty easy to do. Let's look what happens when they don't give us a set of points, but they give us an actual function. So here we have that word domain happening again. And here is what I would think is the most helpful way to think about domain, is to think about restrictions, which is why that Bible verse came to mind. And this idea of domain comes to mind a lot, because the first thing to think about with domain is, what are the restrictions? Because if there's no restrictions, then your domain's everything. Your domain's all real numbers, every number in the world. And so there's two types of restrictions that I think really happen until we get to about chapter 6. But for right now, there's two restrictions. One restriction is if you have anything, so I'll put a number symbol, you can put a variable, over X, or any X on the bottom. That would be bad. And a second type of restriction is a square root with an X inside of it. And why are these restrictive? Well, because if you take the first one, the bottom, also known as the denominator, cannot be 0. If there's an X on the bottom, that entire denominator cannot be 0. That would be bad. And then if you have a square root, the inside has to be greater than or equal to 0. It cannot be negative. Otherwise, we'd be in the imaginary numbers, and it wouldn't be a real solution. It would be imaginary. And so when I go and look at this equation or this function to the right, I don't see any x's on the bottom, and I don't see any x's inside of square roots. And so my domain is all real numbers, which in interval notation looks like this. Every number in between negative infinity and positive infinity. And that's kind of the flow chart that we're going to use for this entire section to find domain. So here's another problem. I'm just going to copy this flow chart over so we don't have to write it again. I'm going to do that probably all day and use this flow chart to say, do I have any x's in the square root, and do I have any x's on the bottom or the denominator? It looks like I have x's in the denominator, so I'm going to use that rule, and I'm going to say, hey, denominator, you cannot be 0. You are not equal to 0. And then we're going to solve that just like we solved a lot of the problems all year. We're going to solve that, and instead of writing the equal sign, we're just going to write a does not equal sign. So 2x does not equal 1, and x does not equal 1/2. But you know what x is allowed to be? Every other number in the world besides 1/2. And so if I put that on a number line, I'm going to put a little circle at 1/2 and say, hey, x, you're not allowed to be 1/2. But you know what you are allowed to be? Every number to the right of it and every number to the left of it. And then we'll write that in interval notation because this is the most common, the most popular, and the notation that we're going to ask you for on tests and homework and quizzes and anything we do. So we start at negative infinity, we walk all the way over to 1/2, and then we unite it with 1/2 comma infinity. And the reason we do that is this little parenthesis united with parenthesis including the same number kind of is like a shorthand way to say cut it out. Cut out 1/2. 1/2 is not in our domain. Everything else is in our domain. 1/2 is not. And then we can look, do we have a square root? We do not. And so because we don't have a square root, we don't have to check the other condition. Here's one with the square root. So I'm going to actually grab that again. I'm going to copy and paste that flow chart because, like I said, it's the flow chart we use this entire section. So there's that flow chart where the domain, we check the restrictions. Here's the two types of restrictions that we're checking for. And so, oh, I see a square root. That means I'm going to follow this blue rule, which says the inside has to be greater than or equal to 0. And then I solve for the inside being greater than or equal to 0 in the same way that we've solved all of these problems all year long. We say 2x, you have to be bigger than or equal to -5. I subtracted the 5 over to the other side. X, you have to be bigger than or equal to -5/2. So it says x is greater than or equal to -5/2, which in interval notation would look like this. Bracket, -5/2, all the way to infinity afterwards. And that's my domain. That is all the numbers, all the real numbers that x is allowed to be. And that's how we find it. I generally say if you can follow that flow chart and understand, I know it's kind of shorthand, but understand what it's saying, then you can find the domain, at least for chapters 2, 3, 4, and 5. Another way to write domain, though less common and we won't use it as much, is the set builder notation, where it's a set of numbers, x, such that x follows the condition to the right of that bar. So this is like the set of numbers such that, that's that red bar right there, x follows the rule that comes right after it. Okay, so here is a number line, and we are just going to use some words, set builder notation, and interval notation to describe that number line. The words are kind of tedious, so bear with me here, but the set builder notation and the interval notation are the ones we're really going to hone in on. So the words would say x is less than or equal to. And then where does it look like x starts as less than or equal to? Right there at that green 2. 2. And in between. And then where is x in between? I'll change colors. X is in between those two numbers. Oh, that should be a soft bracket or a parenthesis. And x is in between -1 and 3, including -1. It's just a way to describe it in words. We won't use that a ton. We won't ask you or test you on how to describe it in words, but it's good for your brain to process the words of what you're doing. I'm going to skip to that interval notation because I think that's the one we do the most, and then we can go back and fill in the set builder. But interval notation would say, oh, that's set. Interval notation would say we start at -infinity. I think you can sometimes I tell my students, hey, imagine like a little guy starting on the left, the same way you read a book, and just move him along until he has to stop. So there you go. You see the guy has to stop right there. So it stops at -2, includes it, and then where does he pick back up? He doesn't pick back up until -1. So pick back up at -1, and then where does he walk to? The guy has to walk all the way over. Oh, he has to stop again at 3. And so he stops again at 3. And so there's interval notation. The most common one, the one that I would ask you to know like the back of your hand. And then for set builder notation, I would build a set. I would say x such that, so this is the set of all numbers, x, such that x follows the following two conditions. X has to be less than or equal to -2. That's based on that green marker. Or x has to be in between -1 and 3, and we include -1 and we don't include 3. And there's our set builder. X is given two conditions. It needs to follow one of those conditions to be valid in the domain. And yeah. All right, let's look at, what about when you get a graph? Instead of a function, they give us a graph. Well, we're going to take domain and we're literally just going to draw straight lines down and start at the endpoint and draw lines all the way down and say, what number do we think those are? And so here it looks like the X domain starts at 1950 and ends at 2000. And there's my domain. But this question, for the first time, asks us for the range. And so for the range, we're kind of going to do something similar. We just have to be a little careful. Instead of going to the beginning and the end, we're going to go from the bottom to the top. And the top doesn't necessarily have to fall at the end. So if I start at the bottom and I go over, the very lowest point of this entire line, it looks like it crosses at like 48 about. So I could say the range starts at about 48. And then how high does it go up? If I go to the very top, I'm not going to the end, I'm going to the top. It looks like it goes to about 90. And per this chart, 90 million people. And so there's my range. So we haven't defined that yet, but if domain is the set of all numbers that x is allowed to be, then range can be defined as the output values or all the numbers that y results as. So like x is your input, x is all the numbers you're allowed to plug in. And y is what does those numbers make the y value or the output. So domain is the inputs and range is the outputs based on those inputs. So here we go. We're going to find the domain. The domain is going to be straightforward like we did earlier. The range, we're going to have to do some thinking, and we'll get to call back to 3.1 a little bit. So for the domain, pretty straightforward. We're going to take the inside. Well, I'll go steal it again. We're going to steal this flowchart again for one last time. Can I copy it? Oh, Shoop. We're going to steal it. We're going to bring it down here. We're going to bring it down here. Shoop. We're going to bring it down here and kind of run a line with it, and that's okay. I'll just erase that line. So again, we have the domain restrictions. We have one restriction that applies to this function, and that is the inside. So for the domain, the inside has to be greater than or equal to 0. Which I'm just going to move the x over and be done instead of moving the 2 over and dividing. So if I plus x to both sides, or add x to both sides, I get x is less than or equal to 2. And what does that look like? That means x is all the numbers less than 2. Now for the range, I'm going to show you a couple different ways to do this, but I'm going to encourage you to do it the first way that we're going to show you. So the first way I want to show you to do the range is to use the toolkit functions that you need to know, which is from the end of the 3.1 video. It's also the end of section 3.1 in your book, and it's a list of about 9 functions that you really need to know what they look like. And so this function is a transformation of the toolkit function you need to know. That's just the square root. In the square root function, we know from the graph, because we all looked at it and we memorized and we spent some time learning those toolkit functions, the square root function kind of looks like this. We don't need to know perfectly, we just need to know it looks like that. It starts somewhere and it goes up and to the right. Now this thing has some stuff happening to it, and so we're going to check those domain values and we're going to see what those domain values are. So what I'm going to do is I'm going to build a table, an x comma y table, and I'm just going to check a couple of my domain values and see what comes up. So the first domain value I'm going to check is that 1 at the very end, 2. If I plug and chug 2 into this equation, so I put a 2 in and I say, what's f of 2? Well, that's negative root 2 minus 2, which is just negative 0, which is just 0. So I get 0 as my terminating y value, or my last y value on this list. Well, let's just move 1 over. Now, keep in mind, based on the domain, we can't move to 3 because 3 would result in an imaginary number. And so we need to move down to 1 and say, what is f of 1? Well, that's just negative root 2 minus 1, which is negative root 1, which is just negative 1. And so I think I can see a pattern happening with my range where it's getting lower. And we could try one more number, maybe try, I don't know, 0 could be the next number we try. And if you plug and chug a 0, you see you get negative root 2. And so I can see my range, the biggest it can get, or the most positive it can get, is that 0 at the top. And so my range is going to be negative infinity. But it's not going to stop at 2 because that's the x value. It's going to stop at 0. And later on this year, we're going to get some practice with transformations of functions, and we'll be able to actually plot that function and say that's the normal function with a horizontal reflection and a vertical reflection and a horizontal shift. And we'll take the original function and we'll say, hey, you need to be shifted horizontally, and then you need to be reflected, and then you need to be reflected again, and we'll be able to see our range come out of that. And look something like that function right there that I just drew. All right, so we have one last implication that comes out of the piecewise, or out of the domain and range talk, and that's piecewise function. That is, these functions that are technically 3 functions in one, split up by, per our Bible verse, some boundary lines. And those boundary lines are going to come from these conditions. And so what I'm going to do is I'm going to draw some boundary lines at those numbers where the piecewise is broken up. So the piecewise is broken up at -1, so I drew a boundary line up and down at 1, or -1. There's boundary line at 4, so I'm going to draw a boundary line up and down at 4. And what this function is then going to do is it's kind of going to act like a funnel, where I'm going to take my input over here, and I'm going to see which of these three that input rings true for. And then I'll use the function from that funnel or that sorting system to plug and chug and plot my graph. So for example, I can show you one example of this, and then we'll move kind of fast. Let's call this top function the blue one. Let's call this middle function the green one. And let's call this bottom function the orange one. And we'll plot those in those colors. And so if we pick a number, any number to plug and chug, I'll go ahead and pick 0 because I like plugging in 0. If I plug and chug 0, so input x equals 0, and I take it to this function, I have to decide which of those conditions is 0 true for. Is 0 less than -1? Is it in between -1 and 4, or is it greater than 4? And it's going to fall into the green category. And so I'm going to say f of 0 just turns into -2 based on the piecewise. And so I'll plot the point 0, -2. And then we'll just do that again with a few numbers. Pick a few numbers in each section. Maybe I'll try 1, and if you plug and chug 1, you'll see 1's also green and turns into -2. And we see if you have those toolkit functions down, you'll see, oh, that's the constant function, the first one on the toolkit list. And that's the constant function that's a horizontal line occurring at -1. Right there, that green horizontal line. And we'll look at those conditions at the end to say it does not include either endpoint. Those are those inequality symbols that don't have the underline or don't have the or equals to condition. And so there's 1/3 of my graph. So maybe we'll change to a different color. Let's try the blue function. We need to pick some points that we think are going to fall into the blue category. So x has to be less than -1, so let's just try x equals -2. And if we plug and chug -2 in, we get -8, because -2 times -2 times -2 is -8. And so I'm going to plot -2, comma, -8 on the graph. And then in order to know what this graph does, I'm actually going to plug and chug my boundary condition to see what happens at the boundary. So if I plug and chug -1 into the blue, it's going to kick back a -1, because -1 times -1 times -1 stays -1. And so I'm going to plot that -1 comma -1, but with an open circle, because the boundaries say open circles. They don't have that underline. And I'm going to connect these dots. And if you remember your toolkit functions that you need to know from section 3.1 at the end, this function would have, were it to be able to continue, look like that. The cubic function, x cubed. But the piecewise said, stop at that boundary condition. Stop at that boundary condition of x equals -1, and also stop at this boundary condition of x equals 4. So now we'll go to our orange function and plug and chug a few orange numbers. What are some numbers bigger than 4? But we want them to work nicely with the square root. So I'm actually going to start with 9, because 9's an easy number to plug in. So we try x equals 9 into the orange one. And we say, what's the square root of 9? Well, it's 3. And so we plot the point 9, comma 3. And then like with the last one, I'm going to plug in that boundary condition knowing that it cannot be equal to, but approaches it and gets really close to it. And so if I plug in 4, the square root of 4 is 2, and I'm going to plot 4, comma 2 on that boundary line, but with an open circle because it does not include the 4. And then I'm going to connect the dots and say, there's my piecewise. And if you look at that toolkit function that you need to know, again, I'm just lobbying for you to go look at section 3.1 again. That function actually starts at 0 and is the square root function that goes like that. But the condition says only start at 4, x equals 4. And there's a graph of that piecewise function. So thank you for watching so far. That was 3.2, domain and range. You're going to have plenty of homework to get to practice this stuff, but I would encourage you, if you have any questions at all, reach out to your instructor. We're here and we're happy to help. And we'd love to make this a experience where you can understand and know mathematics at a deeper level instead of just getting some answers at the end of the day. Thanks for watching, and I'll see you next time.